Hello, I'm Steve Hill, CEO of New Hydrogen. On today's podcast, we have the honor of hosting Dr. Carol Parrish, the Floyd D. and Elizabeth S. Gottwald Professor of Chemistry at the University of Richmond. Dr. Parrish is a luminary in the field of computational science, specializing in data analysis and simulations for drug design, energy, and environmental applications. She's mentored over 110 undergraduate students, authored 70 research publications, and secured a staggering $4 million in research funding. Among her numerous accolades are the 2019 American Chemical Society Award for Research at Undergraduate Institutions and the 2018 State Council for Higher Education for Virginia Outstanding Faculty Award. She's a co-founder of the University of Richmond's Integrated and Inclusive Science Program and the Mercury Supercomputer Consortium. Currently serving as an associate provost for academic integration, Dr. Parrish oversees programs in data science, creativity, innovation, and entrepreneurship, and integrated learning. Dr. Parrish, welcome to our Hydrogen podcast.
Thanks, Steve. I'm really happy to be here.
Glad to have you here. Let's get started with your take on a recent article that you actually sent to me from oilprice.com about a breakthrough in hydrogen storage solutions. The report claims that startups like H2MOF are leveraging AI and cutting-edge research to develop efficient room temperature hydrogen storage solutions. Is AI going to solve our energy problems, or what is the role with AI?
Well, AI is a really useful tool, and it can certainly help scientists to solve our energy problems. And I think that article is a nice but maybe not detailed enough example of how AI can be used to explore a variety of different molecular possibilities before going into the lab and actually testing out those molecules. And so, using AI, literally thousands, if not hundreds of thousands of molecular candidates can be studied for their feasibility to have a certain behavior. In the case of these MOFs, these metal organic frameworks, they were looking at how the structure of the MOF, how the structure impacts the ability to store hydrogen and probably also to release hydrogen.
Yeah, I mean, for the common person who looks at AI, they're using probably ChatGPT or something like that, and we all know that like sometimes it gives hallucinations, right? Like false data. Like, how can academics use that? Do they have a different way to use AI in such a way that they know that the results are reliable?
Yes. So platforms like ChatGPT, they have a database that's sort of frozen in time. In other words, at one point in time, they looked all across the internet and they assembled all of the knowledge that was available. They took a snapshot, if you will. Mm-hmm. And then when you go to ChatGPT and you type in a question and it says, oh, we don't really know because our information is only updated through fall of 2022. That's because that's for that version of ChatGPT, that was the last time they took a snapshot. If you pay more, right, and you get the insider view of ChatGPT, you get a more updated database. What scientists do is they generate their own databases. So again, I'm not familiar with the details of the Stoddard work that I shared with you through that, I think it was called OilWire. So they haven't as far as I know, they haven't disclosed exactly how they used AI to optimize the structure of their metal organic frameworks, but the general approach in that sort of situation is that you would run quantum calculations on some number of metal organic frameworks, but those quantum calculations can be very time consuming. So let's say you run quantum calculations on 100 structures and you get certain properties from all 100 structures, and maybe you have 10 properties times 100 structures. So now you have a database that ChatGPT doesn't know anything about, right? The people who ran the calculations have access to this database. And now they say, okay, we're going to take some percentage of this database and we're going to train a model to predict what a good or a better metal organic framework might look like. And they keep going through iterations of this. So they're basically running their own AI on their own database. And then they get high scoring candidates that look like they're going to in this case, likely absorb hydrogen well and also release it when it's time to release it. And then go into the laboratory and test out those examples.
It's fascinating what you're explaining, and so for everybody listening, this is sort of a building their own database to draw the information from, and then informing the AI as to what kind of results they're looking for. Just like in Chat GPT or some other AI application, if you don't ask a question correctly, you're not going to get a very good answer. Right. And in this phase, you have to know enough to know to ask the right questions of the database in order to get the output that you want. And it sounds like these guys in the article are well on their way to finding some good solutions. Would you say that's an accurate summary?
Yes, but I would take it one step further. Not only do they have to know enough to ask the right question, they have to know enough to generate the right database.
Yes.
For which to ask the question.
That's correct. That's correct. But what this does, though, is really remarkable, because so much time and energy is spent when you go to the lab. You're talking about expense, man hours, time, a lot of wasted time. You could say now that if you can draw all of this information and expedite the process by narrowing down your model, then you have a much more efficient path forward.
That's right. That's right. That's right. And so, my field is computational chemistry, computational science. And in many ways, it's like CAD/CAM, but for molecules, right? They don't go and make 10,000 different cars in order to determine the right, prototype for the next DeLorean. I know I'm dating myself there, but instead they use CAD/CAM to look at all the different possibilities. It's the same thing. We're using CAD/CAM for molecules. You're way ahead of your game, actually. DeLorean's coming out with an electric car. Nice, so nice. There you go. So you are on the cutting edge. That's cool. Well, and so, I mean, this brings up another question that I wanted to ask you about, because it's related. We're hearing about NVIDIA and the rise of AI and the increased computational power that's going to be required to run these AI calculations. And that means that these big data centers are growing as the demand for AI grows. And as these big data centers grow, there's a problem that I think most people on the outside don't know. And these data centers actually require a tremendous amount of electricity to run, as well as they have a heating problem where it actually creates a tremendous amount of heat and they have a liquid cooling system that they run through water through these systems to cool all these machines down so that they can continue operating full steam 24/7 as required. So is there a correlation between renewable energy and this, and I'm thinking hydrogen, we can go down that path in a second, and this sort of increased demand for data centers and this industrial waste heat problem? Well, so certainly, our need for energy and electricity is not going away, right? As more technology becomes integral to everything we do on a day-to-day basis, we're going to need energy and electricity, and we can't keep using fossil fuels, right? We're wrecking the planet, and finding ways to generate, fuel sources like hydrogen in ways that are energy efficient as well as environmentally friendly is incredibly important. And it's true. Not only are data centers getting bigger, but data center, it used to be 10 years or so ago, most of the data centers were either associated with national labs, academic institutions, or big industrial sites, pharma, chemical industry, materials sectors. Now you've probably seen, news reports where, little towns in Texas are being taken over by these data centers, and people are complaining about not only the heat dissipation, but the noise, right? The fans needed, the fans that are necessary to cool these NVIDIA chips when they're running 24/7 like this, with all these channels and lanes in these chips. It's a thing, and certainly we're going to need to, it's all power and cooling. You need to put power in to run them, but then when you run the calculations, it generates heat, and you've got to dissipate the heat.
And as we look more to renewable sources to kind of power these systems, we run into a few problems. And one of those problems is obviously we get a lot of that energy from solar and from wind. And when the sun's not shining, the wind's not blowing, there's no energy from that source. We have to take it from a different place, or we figure out some way to store it and crank it back out again. This is one of the places I see as a great venue for hydrogen, is if we can, and in this article that you said, if they're figuring out how to store hydrogen efficiently, now we're talking about a potential to generate green hydrogen, store it, and then use it in the nighttime hours when there's no electricity. But these data centers are running 24/7 and fill the gap there, which is an excellent solution. It's kind of a virtuous cycle that we're talking about.
Right, for sure, for sure. So one area of research in my lab is exploring using organic-based radical molecules for designing batteries, right? So that would be a much greener way of storing the energy relative to the old battery technology, which has so many inorganic sort of toxic materials.
How's that research going?
It's going pretty well. At this point, there's a lot of fundamental work understanding the structure-function relationship between these molecules that have unpaired electrons, right? We call them radicals. But typically, in order to make an efficient semiconductor, which is needed for a photovoltaic device, we need many of these unpaired electrons, right? So we're developing these polyradicals. And understanding how electrons can flow through these polyradicals will allow organic battery technology to advance.
Are you using kind of your experience with computational science to help solve this problem?
Yes. So in similar ways to as I was describing my speculation for how the MOF people work, we do quantum calculations on these polyradicals, and we characterize the different energetic states. And we're actually just starting a new project where, we've done this now for about 10 to 15 years and looked at the sort of polyradical behavior of approximately 15 different molecular systems. And we have thousands of data points. And so we're developing machine learning models so that we can predict what will be the next organic-based semiconductor without having to do the quantum calculations.
It sounds like a really great way to move ahead, and I think things will accelerate as you do so. It's kind of Moore's law in a different way. It's increasing knowledge rapidly as we find these breakthroughs to help accelerate our learning.
Correct. That's correct.
And if anybody's interested, by the way, who's listening and you're undergrad of some kind, you need to go out and go hang out with Dr. Parrish. Get yourself out, get yourself out to the university and University of Richmond, and enroll so you can learn more about this cutting edge type of application.
Yeah. So thanks for that sort of shout out. University of Richmond is, I would say, relatively unusual because we are an undergraduate institution. We don't have any graduate students in the sciences, but we are, one of my former deans like to say we're a research intensive undergraduate institution. So I would say easily 50% of the students who do research with me wind up as published authors on peer-reviewed publications. So it's a really great sort of training ground for a student who wants to be a scientist.
It's a great head start.
Right.
Awesome. Well, we've covered a lot of ground. Are there any other topics on your mind that you wanted to approach before we wrap up today?
I guess I'd just underscore how important computational work is. AI is all the rage right now, and that's super, super important. But undergirding the machine learning and the AI is being able to do CAD/CAM on molecules, being able to do quantum mechanics or quantum mechanics when you're trying to understand, how reactions occur, or molecular dynamics when you're trying to understand how a polymer folds. Being able to harness computational work in coordination with experimental work accelerates the science, leads to less waste, and is less costly.
Yeah, it's a win-win all the way around. Well, thank you, Dr. Carol Parrish, for your experience, your expertise, your enthusiasm and excitement. Actually, I can just feel it for this field of research. And I think it's people like you that are helping us really move the ball forward here in the world of renewable energy, finding creative ways to use the tools at hand to really advance the cause in many different ways. I can see your research applying in so many different ways. So thank you for joining us today, and we look forward to seeing your research in the future. Appreciate you being on board with us today.
Okay, thank you so much. This was fun. I really enjoyed it.
I enjoyed it too. Thanks for being with us.
Okay, see you.